One of the most innovative and intriguing additions to the Mars rover Perseverance exploration of Mars is the Ingenuity helicopter. Although simple in appearance, this little helicopter is the result of complicated scientific and engineering collaboration. A helicopter flies because when the rotors on top spin, they produce lift, causing the helicopter to rise. The amount of air that needs to be moved depends on how heavy the load is that you are trying to lift and how much air is available. This was the problem faced by scientists and engineers in developing a helicopter that could fly on Mars. Since Mars' atmosphere is only 1% of that found on Earth, the rotors would have to spin very fast, and the weight of the helicopter would have to be very light. Considering all of the electronics and equipment which needed to be carried on the helicopter, it was a difficult problem. But here's how they did it. The Ingenuity helicopter is classified as a technology demo, so a lot of its components are off-the-shelf consumer hardware. In some cases, parts were literally ordered from off-the-shelf retailers. Ingenuity uses an off-the-shelf cell phone-grade laser altimeter from Garmin. After landing on the surface of Mars, the first thing that the rover and helicopter do together is search for and find a suitable place for the helicopter to be released to the surface. The landing place should be relatively flat, as the helicopter's 4 carbon composite landing legs give the helicopter only 5.1 inches of clearance above a level surface. The landing place will be the helicopter's airfield. The airfield is a 33 by 33 foot, 10 by 10 meter region where the helicopter will always take off from and land on, called the Helipad. The Perseverance rover will back up about 50 feet, 15 meters from the edge of the helipad, where it will drop the helicopter's protective shield. The helicopter is now ready to be released by the rover. The rover will release the helicopter inside the helipad. Through a series of explosive bolts and tension releases, the helicopter is brought upright and dropped to the surface beneath the rover. After depositing the helicopter inside the helipad, the rover will back up about 330 feet, 100 meters from the edge of the flight zone. This spot is called Twitcher's Point. Twitcher is a British and now Martian term for those who travel long distances to see a rare bird. Although the helicopter's batteries were partially charged during the trip to Mars, the rover will now complete the charging of its batteries using its solar panel. The helicopter will autonomously charge its batteries and autonomously check that all of its systems are operating properly. Ingenuity's rotor system features 4 carbon fiber blades arranged into 2 4-foot, 1.2 meter counter-rotating rotors that spin up to 2,400 RPM, or 40 times per second. Not only does the helicopter have to be super lightweight, but the rotors must be moving incredibly fast. But they can't go too fast. If you keep going faster and faster, the blades start approaching Mach 1. They start wanting to go supersonic, and you don't want them to even go transonic, because you get a lot of turbulent effects. Ingenuity's blades shouldn't exceed the speed of sound, however. They'll reach less than 0.7 Mach. NASA was also concerned about the phenomenon of blade flapping, which is caused by flexing of the rotor blades above and below the plane of rotation. Earth's thick atmosphere would normally dampen blade flapping, but that would not be possible in the thin atmosphere of Mars. A traditional rotor design would have likely torn itself to pieces on Mars. So the blades on Ingenuity were designed to be extremely stiff, while at the same time being thin, lightweight, and very broad across the blade root, to provide the extra lift needed in the thin Martian atmosphere. The blades are built from a composite of carbon fiber skins over a molded foam core. For flight control, Ingenuity uses a pair of swash plates. Each titanium swash plate is controlled by a trio of tiny servo anchored to the rotor mast and connected to the rotor using connecting rods. They change the angle of the rotors, providing directional control of the helicopter. The rotors are controlled by off-the-shelf 10mm diameter DC motors that are responsible for moving the swash plate and adjusting the inclination of the rotor blades. The two motors are of the brushless DC design. The special hand-wound rectangular wire and coil count makes the motors very efficient, light, and compact. Since Mars' atmosphere is only 1% of the density of Earth's atmosphere, its rotors must operate in turbo mode all the time to stay aloft. Processors, therefore, must be very power efficient. Ingenuity is powered by a 6 off-the-shelf lithium-ion battery system that is recharged daily by the solar array located atop its rotor system. Solar cells in the array are optimized for the solar spectrum encountered at Mars. The solar panel can fully recharge the onboard batteries over one Mars day. The stored energy is then used to operate heaters for the cold Martian nights, communications, and also power the helicopter during flight operations. About 1/3 of the power is used to keep the helicopter warm during the night, and 1/3 is used for electronics, cameras, instrumentation, and communication. The rest, about 350 watts, is used for the 90-second flight. The square box above the helicopter's landing legs is called the Helicopter Warm Electronics Box, or HWEB. It uses a combination of thin film heaters and a layer of polyimide insulation to both absorb as much solar thermal energy as possible while reducing heat loss from inside of the box to the Martian atmosphere. It is about the size of a box of tissue. The electronics needed to run the helicopter, including computers, batteries, flight controller, cameras, sensors, navigation system, heaters, altimeters, and telecommunications hardware, are all housed in the thermal management box. Ingenuity has some interesting electronics that provide all the processes needed to make the Ingenuity helicopter's performance possible. Qualcomm, best known for its processors that power smartphones, supplied smart robotics semiconductors to power the Ingenuity helicopter. The main computer on Ingenuity is a Qualcomm Snapdragon 801 processor that includes a quad-core CPU, a GPU, and a 5.5 megapixel downward-facing image signal processor. The computer controls navigation using Mars surface geography features tracked with the camera. The chip itself is not much different from other Snapdragon chips used in billions of smartphones, and is often used for drones and robots. The helicopter carries a Garmin LiDAR Light V3 laser altimeter to determine altitude of the helicopter, as well as an inclinometer that is used to establish how the helicopter is tilted relative to the ground. In addition, the helicopter has a sequencing engine on board. The guidance part of the flight is planned on the ground as a series of waypoints. When NASA wants the helicopter to fly, the guidance software on board Ingenuity takes over and executes taking off, traversing to the different waypoints, and then lands. This means that the flights are pre-planned very specifically, and that the helicopter is not executing complete autonomy, but a sort of halfway autonomy. As it flies, however, it is autonomously trying to make sure it stays on that trajectory in the presence of wind gusts or other things that may happen in the Mars environment. The guidance software is always making sure that all of the sensors are healthy and producing good data. The helicopter runs on a Linux operating system and is the first time that Linux will be flying on Mars. It is the same software framework that was developed for CubeSats and instruments. The software framework that's flying on the Mars helicopter was open sourced a few years ago, so you can get the software and use it in your own project. There are some pretty sophisticated cameras on board the helicopter, including a descent camera and color camera that will be taking images of the surface of Mars. The black and white camera is a 0.5 megapixel downward-facing framing navigation camera on the bottom of the fuselage. It is used by the onboard navigation system to see how much lateral motion the helicopter is achieving, and with the inertial measurement unit, sends data about Ingenuity's pitch, yaw, and roll to the onboard computer. It is all part of the flight control system. This camera is black and white because it is easier to see exactly where the helicopter has landed. There is also one color 13 megapixel horizon-facing terrain camera on one of the bottom edges of the fuselage. This camera is very similar to the camera found on a cell phone. During flight, the helicopter will communicate with the rover and image the surface. Data acquired during flight is transferred to the rover and later relayed to Earth by the rover. The antennas of NASA's Deep Space Network send commands and other data from Earth directly to the rover or to Mars orbiters. If data is sent to the orbiters, then the orbiters relay those transmissions onto the Perseverance rover. The helicopter cannot transmit or receive directly from Earth, so the rover's main computer relays the commands and data to the helicopter base station on the rover, which then transmits them to the helicopter. Conversely, the base station collects transmissions from the helicopter and routes the data back to the orbiters or directly to Earth. The Mars helicopter base station is located on the side of and inside the Perseverance rover. This is seen here as the upper gold-colored box near the back of the rover. Communications to and from the helicopter are made through a Zigbee radio link over 900 MHz Sci-Flex chipsets mounted in the rover and the helicopter. There are 3 main pre-planned flights with the helicopter landing in the same spot that it took off from. If time allows and a different area looks safe, engineers can try landing in a different area. The first test flight is scheduled to launch about 11 a.m. local Mars time, when winds in the area are expected to be the lightest. 11 a.m. gives the helicopter the morning hours to warm up after a cold Martian night, yet give plenty of daylight for operations. The helicopter will check with the instrument META on the rover for information on wind data. The helicopter will have autonomously run through a series of pre-flight checks and run the rotor system to around 2400 RPM. If everything remains go, the computer will command the rotor blades to change their angle or pitch, taking a deeper bite into the Martian atmosphere. The first attempt at powered controlled flight on Mars will begin. Ingenuity will climb about 3 feet per second to an altitude of about 10 feet. Then it will hover for about 30 seconds and descend at about 3 feet per second until touchdown. Flight Test 2 will be expanded to include climbing to 16 feet and then flying horizontally for a few feet, descend, and land within the airfield. Images from the helicopter's navigation camera will later be used to evaluate the helicopter's navigation performance. Flight Test 3 will be expanded to test the helicopter's ability to fly farther and faster, up to 160 feet from the airfield, and then return. Flight Test 4 and 5 will be based on data returned from the first 3 tests. The flights could further explore Ingenuity's aerial capabilities, including flying at a time of day where higher winds are expected and traveling farther downrange with more changes in altitude, heading, and airspeed. A question that has been asked is, what if the helicopter lasts longer than anticipated and the 30-day window for operation passes? Does that mean that the rover will end up just driving away from a perfectly functional Mars helicopter? The answer is yes, because the rover has to get on with its primary mission. Just as Sojourner was the first technology demonstration that paved the way for all of the much more capable and larger rovers that followed, the Ingenuity helicopter will pave the way for future autonomous flights. For the future, NASA will consider incorporating small helicopters into mission plans for future robotic and human exploration of Mars. Taking to the air would give scientists a new perspective on a region's geology and allow them to peer into areas too steep or slippery to send a rover. Future generations of Mars helicopters could provide a supporting role as robotic scouts, surveying terrain from above. These future helicopters could also collect samples or carry an instrument payload for in situ scientific investigation. In addition, a future Mars helicopter could carry light but vital payloads from one site to another. Future concepts include swarms of craft that fly together and work cooperatively, or a larger flight vehicle that could independently travel from location to location, enabling a new type of otherworldly exploration. The Jet Propulsion Laboratory is studying the potential of Mars helicopters, weighing up to 33 pounds. Scientists are attempting to push the frontier and get aerial mobility as a part of exploration. NASA is currently developing the Dragon quadcopter, scheduled to explore Titan in 2026. Ingenuity is truly a scientific and engineering marvel and will lead the way for the next step in exploration of our solar system.